All right, I'm going to erase all of this math and we're going to talk about what these terms actually mean. So in the Michaelis-Menten equation, V naught describes the initial velocity of an enzymatic reaction at a particular substrate concentration. The V max is going to be the maximal velocity that the enzyme is able to achieve, which occurs when the enzyme is entirely saturated by substrate. The Michaelis-Menten constant, which is denoted here by Km, is derived based on a ratio of how readily the enzyme-substrate complex forms and how readily it breaks apart. The Michaelis-Menten constant is also the substrate concentration at which the initial velocity is equal to half of the maximal velocity. You can work this out mathematically if you want by subbing for 1/2 V max in the V naught part of this equation. The Michaelis-Menten constant ends up being a good proxy for how tightly an enzyme is able to bind to a substrate, which is known as the affinity. When the Michaelis-Menten constant is low, that means that even a low concentration of substrate is sufficient to get the enzyme to half of its maximal velocity, which suggests that the enzyme is able to bind to the substrate very efficiently. On the other hand, if the Km is very high, that means there needs to be a lot of substrate around for the enzyme to reach half of its maximal velocity, suggesting that the enzyme does not bind to the substrate very efficiently. Being able to interpret the meaning of the Km is an important step 1 skill. It's also important to be able to interpret the Vmax and the Km off of a graph of a Michaelis-Menten curve. So over here we have a graph where on the y-axis we have the initial velocity, and then on the x-axis we have the concentration of the substrate. Now the only enzymes that are contributing to a reaction proceeding are going to be the ones that are bound to a substrate forming that enzyme-substrate complex. So at low substrate concentrations, the velocity is going to be very, very low. For example, when there's no substrate around, the velocity is going to be 0 because the enzyme won't be able to turn any substrate into product. When there's a little bit of substrate around, some of it will bind and the reaction will proceed, but the reaction won't be proceeding as fast as it would be if there was a lot of substrate around. As the substrate concentration increases, the velocity will increase in a linear fashion. This linear relationship between the velocity and the substrate concentration is known as first-order kinetics, which occurs when the velocity is dependent on the substrate concentration. This is going to occur in situations where the concentration of the substrate is relatively low. Eventually, as the substrate concentration increases, all of the enzymes will be bound to a substrate, and any additional substrate that's added at this point isn't going to have any available free enzyme to bind to. This is known as enzyme saturation, and at this point, the velocity can't increase anymore. You can see that here as this curve starts to plateau. This plateau, where the velocity is independent of substrate concentration, is known as zero-order kinetics. And that's going to happen when the substrate concentration is a lot higher than the enzyme concentration. You can't see it on this graph, but for the sake of completeness, I'll mention that second-order kinetics occurs when the velocity is dependent on the concentration of two different substrates. Let's discuss now how to identify the Vmax and the Km on this graph. The Vmax is going to be the maximal velocity, so that means it's the highest velocity that the enzyme could possibly reach. And that's going to be signified by this plateau here, which occurs when the enzyme is saturated. So if we follow this plateau out to the y-axis, that's going to get us the value of the Vmax. In order to find the Km on this graph, we need to remember that Km is the substrate concentration at which the enzyme is able to do half of the maximal velocity. So the first thing we'll do is identify half of the Vmax on this graph. So if this here is the Vmax, half of the Vmax is probably somewhere here. And we'll follow that out to where we meet the curve and then drop down to the x-axis, which will get us the substrate concentration at which the enzyme does half of the maximal velocity, otherwise known as the Km. Alright, the last thing I want to talk about in this video is Lineweaver-Burk plots. Lineweaver-Burk plots are the exact same thing as the Michaelis-Menten equation. All we've done is taken the reciprocal of it. And the point of this is you wind up with something that looks like a line instead of a curve, and it's easier to look at visually and easier to analyze statistically. So remember that the standard equation for a line is y equals mx plus b. So the y here is going to represent the changing values on your y-axis. The x will, of course, represent the changing values on your x-axis. The m is going to be the slope of your line. And the b is going to be the y-intercept. When you take the reciprocal of the Michaelis-Menten equation, you end up getting that 1 over v naught is equal to Km plus the substrate concentration divided by V max times the substrate concentration. And then you can separate this term out and you end up with Km divided by V max multiplied by 1 over the substrate concentration plus the substrate concentration divided by V max times the substrate concentration, and then you can just cancel out these terms, so you end up with 1 over the V max. And now if we consider our y-axis to be 1 over V naught, which you'll see on our graph here, and our x-axis to be 1 over the substrate concentration, and you can see that on our graph here as well, the rest of your terms end up making this a line graph. So the Km divided by V max is going to be your slope, and 1 over V max is going to be the y-intercept. So now you end up with a line instead of this curve, and it's also important to be able to determine the Km and the V max from this kind of graph, and it's quite nice because the intercept will actually tell you the V max and the Km. So like we already talked about, the y-intercept is going to be the reciprocal of the Vmax. So if you have a Lineweaver-Burke plot, all you need to do to find the Vmax is look for the y-intercept and then take the reciprocal. And then the x-intercept is going to tell you the Michaelis-Menten constant. So the x-intercept will be -1 over the Km. So if you can find the x-intercept, all you need to do is take the reciprocal and multiply by -1 in order to get the Michaelis-Menten constant. You can see how that works out mathematically by substituting 0 in for 1 over V naught in the equation, and then solving for 1 over the concentration of the substrate. We've covered a lot of really important concepts in this video, and knowing what the Michaelis-Menten equation is really important for step 1. It's also important to remember that the Vmax is the maximal velocity, which occurs when all of the enzyme is saturated. So that's going to be at those high substrate concentrations. The Km, or the Michaelis-Menten constant, is going to be the substrate concentration at which the velocity is half of the Vmax, and that makes it a good proxy for enzyme affinity for a substrate. Remember that lower Km values mean higher affinity or better binding. You should also know how to find both of these values on a Michaelis-Menten curve and a Lineweaver-Burke plot. On a Lineweaver-Burke plot, the y-intercept is going to be 1 over the Vmax, and the x-intercept is going to be -1 over the Km.